So representing the carbon compound, there are many ways to do it. Of course, you see all sorts of different ways of doing it. And so the main ways are the space filling model, which is there on the left. It sort of feel like just the balls kind of just merge together, forming weird sort of hemisphere shapes. And that's the space filling one. The ball and stick model, which is what I showed you just then. It's just, balls and sticks representing bonds. The Lewis dot diagram, which we're all familiar with by now. We can draw Lewis dot diagrams. Structural formula. So structural formula, again, we should be familiar with. It's just bonds represented as a single line rather than two dots. And the dash and wedge. So the dash and wedge is sort of a newish one or a more advanced one. And you may not be familiar with it, but we'll go through it later and show you how it works. Okay? So the space filling model. And there it is again, the space filling model. It shows the shape and relative dimensions of a particular molecule. So we have a shape here, but you can see that the carbon is much bigger than the green one is much bigger than the white one. So this space filling model helps you get a feel for how big a certain atom is compared to another. So atoms are represented by spheres, so the green or the white in this case. And the radii are proportional to the radii of the atoms. So if the radii of one atom is enormous and the other atom is very small, then you'll notice that difference. You'll get a very big sphere on one side and a very small one on the other. The center to center distances are proportional to the distance between the nuclei. Okay? So by center to center distance, I mean the center here compared to the center here is proportional to the distance between the nuclei in the actual chemical. So what this doesn't do is it doesn't show the number of chemical bonds. Okay, so the number of chemical bonds or the bonding structure is implicit in this kind of diagram. So the ball and stick model, it shows 3D position of atoms and bonds. Okay, and atoms are represented by spheres again, and bonds are represented by straight or curved rods. So in this case, the rods being these parts. Okay. So radii of spheres are not proportional to the bonds. And important in showing bonds, but not atom distances. Okay. So the ball and stick model has the advantage of it shows you the bonding structure explicitly, but it doesn't show you atom distances, nor does it show you the proportionality between the radii of the spheres. Okay. Lewis dot diagram, so we're familiar with this at the moment. So this is a typical Lewis dot diagram. Shows the valence electrons in an atom. Okay. Shows the bonding between atoms as well. So it shows bonding explicitly once again. And it also shows you lone pairs of electrons, which are important in the VS-EPR theory, as well as in future topics relating to coordinate covalent bonds. So again, lone pairs are very important. It shows the position of the atoms in the structure of the molecule. Okay, so it shows you where they are placed within the molecule. But however, it can't show you the shape of the molecule. Okay, so for instance, if something was more complex than this, we would only be able to represent it in 2 dimensions, so up and down, and left and right. Whereas if it was 3D, we'd have no way of showing that with a Lewis dot structure. So that's the major disadvantage of this method. Structural formula, again, 2D graphical representation of the molecule. So here we go. Here's the same molecule that we saw in the Lewis dot structure one. Shows the position relative to each other. So like the Lewis dot structure, it's the same. Shows the bonds. Doesn't show the valence electrons or the relative distance or size. So it suffers from many of the same deficiencies that the Lewis dot structure does, except it's a little bit simpler in the sense that you only have to draw lines rather than lots of dots. And the dash and wedge representation. So this shows the structure in full 3 dimensions. So a straight line shows the bond in the same plane as the page. So these bonds here are all flat against the page. Okay? Wedges show the bonds coming out of the page. So this H would actually be coming out of the page like this, so towards you guys, and towards you guys again, right? And dashes show bonds that go into the page, right? So they're going away from you and this one's going away behind this C atom. Okay, so they're going actually behind this molecule. So the real advantage of this is that in a two-dimensional diagram, you can actually represent a three-dimensional structure. Okay? And this is a typically used form for modern chemists, and they'll use it all the time to show you these kind of compounds. Okay? So that wraps up today's lesson on representing carbon compounds and the structural forms. So we talked about the various models from the space filling to ball and stick, Lewis dot structure, structural, and dash and wedge. And so hopefully you can see how each of these has advantages and disadvantages. And in order to communicate effectively between chemists, we need to know how to use all of them.